All right, so back to finish section 4.6 with story problems. Now, don't be too fearful of these story problems. Yes, they look kind of long, a lot of words, looks like a whole paragraph for most of them. But all of these story problems have a very, they have the same format or template. They are describing in here a proportion that has one missing or unknown piece. In each one, there should be a very obvious rate or ratio in the problem. Usually it's going to be a rate. Okay. And then they'll give you another part of the rate. You kind of need to write the proportion, piece it together, using an unknown like n or x. I don't care what you want to call the variable. You can put your name down there for all I care. But you need to use something to represent the missing or unknown piece in the proportion. Once you have the proportion written, you're good to go. Just cross multiply and solve as we've been looking at in the last few examples. Okay, so let's check problem 40 on page 267 as a first example. Okay, so let's read this. It says, Lester owns 2 large farms with square plots of the same dimensions. He subdivides one farm into 3 equal parcels and the other into 4 equal parcels. For the same price, you can buy either 2 of 3 parcels or 3 of 4 parcels. Do the parcels yield the same amount of land? Now, this is a very interesting proportion because there really is no unknown here in this case. What they do is they give you one ratio in this case, where you have 2 out of 3 parcels. And then they give you another ratio, 3 out of 4 parcels. They want to know, are these things giving you the same amount of land? Okay, the lots he has for his farm are the same size, but he's taking one and dividing it into 3 pieces and the other and dividing it into 4 pieces. And he wants to know, well, if I'm taking 2 of these 3, or if I'm taking 3 of these 4, is this really the same amount of land in each case? Well, how do you figure that out? Well, write the proportion, put a question mark over the equal sign, kind of like they did in problems 15 through 24, and figure out if this is a valid proportion. Okay, how do we figure out if it's valid? Well, kind of like when we solved equations, we need to cross multiply. So we're going to take 2 times 4 and check to see if that is equal to 3 times 3. Well, close, but no cigar. No, these are not equal amounts of land if this is how he is dividing and choosing his parcels. Okay, if he's dividing this one into thirds and taking 2 of them, this one into fourths and taking 3 of them, no, this is actually a little bit more land than this. Okay. So kind of an interesting problem because it's not going to really fit the mold of what we're going to see for the most part. What actually fits the mold of what we'll see for the most part is something like 44. But this was kind of an odd one because they gave you everything you needed to write out the entire proportion, no unknown or missing pieces. They just simply wanted to know, is this a valid proportion? Are these, if I divide the lands out this way, let's say 2 out of 3 or 3 out of 4, are these equal amounts of land? No, it's not. The 44 is more typical of what you're going to see. So it starts off with kind of a condition and then asks a question. If a 200-pound man can have 1,000 milligrams of a certain kind of medicine each day, how much can a 120-pound woman have? Okay. Well, maybe sound kind of sexist, but obviously there's some legitimate biological necessity behind this. So what they start off with is a known rate. Okay, right away they hit you with a known rate. They say a 200-pound man is able to have 1,000 milligrams of a certain drug. Okay. Now, kind of all other things being equal, I know certain kind of tolerances are different from person to person, but generally speaking, question is, if you have a 120-pound woman, just how many milligrams, I don't care if you want to use N or X, it doesn't matter what you do for the unknown. The question is, if you're only 120 pounds, generally speaking, how many milligrams should you be getting? Okay, so not entirely sexist. I mean, if this is a 120-pound man, it'd be the same sort of deal. How many milligrams should you give to a 120-pound person if you know that a 200-pound person, typically speaking, tolerates 1,000 milligrams very well? Okay, so they gave you almost everything for the proportion. They gave you a well-known rate, and then they gave you part of another rate. When you write out your proportion, the very important thing to do is that you have the same units on the tops and bottoms of your rates. Okay, this will ensure good integrity as you go through this and work things out. The units will work out just correctly. You don't have to worry about them, but they will technically work out if you were to do unit analysis on this. So, start with the known rate, or possibly ratio. Say equals. And then again, check to see the units on the other known piece of the other rate. In this case, they told us the weight, so I put that up top. I matched it with the weight. Okay, the unknown is how many milligrams should I give a person of this size? Well, as usual, to solve a proportion, whether it's got all pieces known or one unknown piece, cross multiply. So I get 200 times x equal to 1,000 times 120. Again, I'm ignoring all the units. Technically, they would work out even if you brought them along. But more, this isn't a science class, so I'm not really worried about that. But, unit analysis is kind of an interesting thing that if you get into some little basic chemistry, biology, or whatever, you might actually get into some of that stuff in those classes. It's not terribly important, though, for what we're doing here. We know X represents milligrams, bottom line. That's what I'm solving for. So I've got 200x equal to 1,000 times 120 is 120,000. Okay. So get my nice inline equation as usual after cross multiplying, doing some of the, evaluating of the individual products. Now let's divide by 200 so I can figure out what x is, not what 200x is. So these will cancel out. You notice I've divided by 200 once on each side of the equal sign. And this is where you can just use your calculator. Again, this is Unit 4 stuff. Technically, you can use your calculator the whole way. You still have to show some work and steps in between. Don't get me wrong. Show me that you actually know what you're doing here. But if you take 120,000 and divide it by 200, you'll get 600 for the answer. Okay. You cross off these two zeros. It's really like you're dividing 2 into 1,200. So 600 milligrams. They know, generally speaking, a 200-pound person can tolerate 1,000 milligrams of this. So if you're only 120 pounds, you should probably only be receiving 600 milligrams of this medication. Okay. So again, this is a very common format. They'll usually hit you right away with a well-known rate. Go ahead and write that out in fractional form and then put an equal sign. Then keep reading. They'll give you one other piece of information about the other rate. In this case, they gave us the weight of the person. Okay, I want to make sure that matches up with the weight of the person and with the well-known rate. Okay, and then use an unknown x, and I don't care what you use. Okay, whatever variable you fancy. Use that to represent the unknown piece. And as always, the way we solve a proportion, cross multiply, evaluate any products as needed, divide both sides by the coefficient of your variable. You should have your answer. Okay, let's flip the page to 268 and check out a few examples here. And let's start with problem 50. So for those of you that maybe like to overindulge like myself, they say, if 100 grams of ice cream contains 15 grams of fat, how much fat is in 260 grams of ice cream? Okay. It's a good question, except I usually eat way more than 260 grams even if I have ice cream. Let's see. So they said 100 grams contains, excuse me, 100 grams of ice cream contains 15 grams of fat. So I'll use IC for ice cream. Let's write out fat. So this is the well-known rate that we are given. 100 grams of ice cream contains 15 grams of fat. So the question is, well, how much fat is in 260 grams of ice cream? Okay. And just for variety, I'll use n here just to show you it doesn't really matter what you call the variable. So again, this was the well-known rate they gave us over here. And this is kind of the question here. Well, what if I've got this much of this amount? Okay. In this case, they want to know, in this case, how much ice cream. So they want to know how many grams of fat you'd have if you had this much ice cream. So again, I've got grams of ice cream on the top, grams of fat on the bottom. Go ahead and cross multiply, just using the numbers and the variables. So we have 100 multiplied to n. That should equal 15 times 260. Okay. So obviously we'll just usually write this as 100n sans the multiplication symbol. 15 times 260 would be what? 1380 plus 2600, which would be 3980, I think. I'll just give that a quick check over here. No, 3900. Oh, whoops. Sorry, I don't know why I got an 8 in there. Yeah, it should be 1300 plus 2600, which is 3900. Yeah. All right. Sorry, long day. So, after cross multiplying, after correctly evaluating our products, we get 100n equals 3900. Again, at this point, to solve for the unknown or the variable, go ahead and divide by its coefficient on both sides of the equal sign. And in this case, it looks like we get n equals 39. So if 100 grams of ice cream has 15 grams of fat, 260 grams will have 39 grams of fat. So again, the main thing in taking these story problems and breaking them down, not that the last two have been terribly long, but generally speaking, early on they should hit you with a well-known rate, possibly a ratio. And then we'll give you another part of that rate that should link up with one of the two items they described previously. Okay. All right, let's try 52. I'm talking about map scales here, kind of maybe a forgotten art with GPS being so prevalent. But 52 reads as follows. They say, on a tour guide map of Ohio, 2 inches on the map represent 260 miles. So the question is, how many miles do 3 inches represent? Okay. So the first thing they tell you is that 2 inches is to 260 miles. As 3 inches is to, I don't know. Okay, so we want to figure out how many miles 3 inches would represent in real life here. Okay, so again, this was the well-known rate that they gave you early on in the problem. And then they followed it up with a question, if this is the case, well, what if you have 3 inches on the map? What kind of real life distance are we looking at here? So again, not knowing that amount, presumably put the variable in its place when you write the proportion. And to get this out of the proportion model into kind of a nice looking equation, cross multiply. So take 2 times n and set that equal to 260 times 3. Or more simply, 2n equals 780. And as usual, once you get to this point, go ahead and divide both sides by the coefficient of the variable. Complete your division, and you should have your answer. Okay, if 2 inches is 260 miles IRL, or in real life, 3 inches should be 390 miles of distance. Okay. So again, kind of maybe a forgotten skill. Used to be kind of common once upon a time, as people usually carried road atlases in their cars or something. But still, if you're going out hiking and someone's kind of mapped out the area, that could be a useful technique to have tucked away in your back pocket. Let's try 56. Metallurgy. Renak is a metallurgist and often must determine the amount of zinc or copper in specific quantities of metal alloy. If the ratio of zinc to copper in metal alloy is 3 to 13, how many pounds of zinc are present if there are 260 pounds of copper in the alloy? Okay, so this is a slightly longer problem. And they kind of give you a lot of fluff here, to be brutally honest. Okay, whoop-de-doo. Renak is a metallurgist. He's got to determine this or that, blah, blah, blah. Then they tell you, starting in the second sentence, if the ratio of zinc to copper is 3 to 13. So I think Z, N, and Cu are the periodic table symbols for zinc and copper. So they give you that ratio right off the bat in sentence 2. Okay, the ratio of zinc to copper in your alloy. They want to know how many pounds of zinc are present in this alloy if there are 260 pounds of 260 pounds of copper in the alloy. So here, our unknown is zinc. How much zinc am I using if I've got 260 pounds of copper in my alloy? Okay. So again, only the real difference from some of the others that we've had here is that the unknown is not on the bottom. It's actually on top. The unknown is zinc. And the way they originally phrased the ratio of zinc to copper, they gave us zinc first, copper second, and my unknown amount is zinc. So make sure that unknown goes up in the top. The known amount is copper, and that should go on the bottom, at least the way they stated the first rate. It's okay if you want to invert these, This would also work to solve the problem as well. Okay, if you invert both of these fractions on each side of the equation, this would also be just fine. Okay, they'll both lead to the same answer. You'd still be taking 13 times x either way, and 3 times 260. Okay. So 3 times 260 is equal to 13 times x. Okay. Well, as I saw in the last problem, actually, 3 times 260 is 780. The only difference, instead of dividing by 2 on both sides, we want to divide by 13 on both sides. And if you do this division, 13 happens to go into 78 6 times evenly, so we'll end up getting 60 for the answer. Okay. So again, most of the time, the vast majority of these story problems in section 4.6, they start off with a known rate or ratio, a little bit more commonly a rate, as we've seen in these examples. And so go ahead and start writing that fraction, follow it up with an equal sign. Okay. After that, they're going to tell you a known piece of another rate or ratio. Okay. So here I had this ratio, in this case, of 3 to 13. Whatever units of measurement they had, 3 pounds of zinc to 13 pounds of copper. I don't know, they didn't say, they just said 3 to 13. But then they gave us actual weights here. I've got an unknown amount of zinc for 260 pounds of copper. Okay, so this was a known ratio in this case. Here I had one piece of the ratio over here. The other part was unknown. Okay, make sure to write some labels here so you know what goes with what. Like I said, you can invert both these fractions. You still have zinc to zinc on the bottom, copper to copper on the top. What will not work, okay, what will not work is if you happen to invert one fraction but not the other. Okay, this would not work to solve this problem at all. Okay, you need to be comparing within the proportion. You need to be comparing apples and apples on the top, oranges and oranges on the bottom. Okay, so. I don't know if there's really anything else much to do here in this section. They're all very similar to what I've already gone over. I don't think there's anything. I know 59 and 60 have some ever so slightly larger numbers, but they're really about the same as everything else we've worked on. So I think it's a sufficient number of examples to conclude 4.6. But if you have any questions, as always, feel free to email me.